Suswagatam, Suswagatam, Suswagatam. I, Dr. S.G. Kulkarni, Department of Physics, welcome all of you here. I welcome Professor Ashutosh Kotwal, who has come from USA to address us. I welcome Dr. Sharad Gunte, who is Chairman of Governing Council and Governing Body of Deccan Education Society. Dhananjay Kulkarni, Professor Dhananjay Kulkarni, who is Secretary of Deccan Education Society. Principal Ravindra Singh Pardeshi sir, Principal of this college. In short time, Sri Jayanta Sastrabudhe will be joining us. I also welcome all scientists, professors, students, common science lovers in and outside India, in and outside Pune, who are watching this program online. So I welcome all, and I am very much glad to see you all here in spite of heavy rains and all traffic jams. So welcome again. Let us start our program with the prayer of Vijnana Bharati. I invite senior scientist, retired senior scientist and group director of DRDO, Sri Kashinath Devdar, to recite the Vijnana Bharati prayer. Kashinath Devdar, sir.
Om Purnamada Purnamidam Purnat Purnamudachyate Purnasya Purnamadaya Purnameva Vashishyate Ishavasyamidam Sarvam Yatkincha Jagatyan Jagat Tena Tyaktena Bhunjitha Magrudah Kasya Svidhanam Vidyancha Yastadvedo Bhayam Sah Avidyaya Mrityum Dirtva Vidyaya Mritamashnute Sarvepi Sukhinas Santu Sarve Santu Niramayah Sarve Bhadrani Pashyantu Ma Kaschid Dukkha Bhag Bhavet Om Shanti Shanti Shanti.
Thank you, Kashinathji. Really all will be happy and all will have peace of mind if the science progresses in a positive direction. And so we have started our program in a positive note. I now invite Principal of our college, Dr. Ravindra Singh Pardeshi. He is a senior geologist, a scientist in geology, and last 25 years he is life member of Deccan Education Society and member of governing body of Deccan Education Society. He is very popular among students and he knows majority of the students by first name. So I invite Dr. Ravindra Singh Pardeshi to say a few words about this program and this college.
Thank you, Dr. Sunil. Honorable Chairman, Dr. Sharad Gunte, Professor Ashutosh Kotwal, Sri Dhananjay Kulkarni, all scientists fraternity. I am very glad to welcome one and all to this historic amphitheatre where the Ferguson College has a long legacy, rich legacy, and we are very proud to carry this heritage. And Professor Ashutosh Kotwal, who has been a name in the field of the new theory which is coming up or which has already been established and giving challenge to the standard model theory, especially in the material physics or otherwise. Before, of course, as you know, earlier he was in the same very campus, in the same very hall on 20th of February 2016. That time also we were very happy to receive him here, and we listened to him because that was the Higgs boson or the God's particle, whatever things are there. Of course, I am a geologist, so I may not be going to be will be telling you about it. Of course, we are very eager to listen to Professor Ashutosh Kotwal. But this very amphitheatre, which has a long legacy and heritage, as I said, the first Nobel laureate of India, Dr. Chandrasekhar Venkatraman, visited us on the occasion of 50 years of Ferguson College, that is Golden Jubilee, in 1935. Dr. Rabindranath Tagore visited us, and then, of course, Dr. Raja Ramanna, Govind Sarup, and many more, of course, and that is how our students always are getting the benefit of such scientists who visit us and share their experiences, and therefore we are very happy and fortunate to say that we are able to connect with all scientists who are coming from different parts of the globe. So I will not, of course, take much of time because we are eager to listen to the talk, and therefore today's speaker, Ashutosh Kotwal, his family members, and all scientists, I once again welcome and conclude. Thank you.
Thank you, sir, for your very brief note. I would like to tell you, sir, and authorities of DS that Deccan Education Society decided to telecast this program in all units of the society, and then we decided that why should we restrict such a personality to only DU Society. So then we requested DU Society to broadcast this program so that it can be watched all over India and outside the India also, because one of the organizers of this program is GIST, Global Indian Scientists and Technocrats. So right now, all the people outside India are also watching this program. I hope the link is now okay and working. And people all over Maharashtra are watching this program, all over India are watching this program. We have connected all the physics departments in all the universities, university departments in India. All the universities in Maharashtra have, vice chancellors have particularly written personal letters to all the colleges that this program should be watched in the seminar hall together by physics fraternity, so that you can have interaction. So this is a very good piece of information that I have right now. I hope Sri Jayantrao Sahasrabuddhe has arrived. I request Jayantrao Sahasrabuddhe to be on dais. Now I invite Professor Dhananjay Kulkarni, who is Secretary of Deccan Education Society, to have few words about Deccan Education Society and its role in this program. Dhananjay Kulkarni is also a physics teacher, so we are very fortunate to have many physics people over here. So I invite Dhananjay Kulkarni to give some note about the society.
Good evening to one and all, and all those who are present in the amphitheatre as well as those who are watching this program online all over the globe. So once again, welcome to all. Now today we are fortunate that Dr. Ashutosh Kotwal, Professor Ashutosh Kotwal is going to deliver lecture, and his discovery is definitely going to make a lot of changes in the modification in the standard model theory, and that will be another big challenge. So his theory or his experimentation has not only discovered something but has made scientists to think something different and to modify the theory. So he's going to make a lot of change in the physics and the theory of the physics too. So Deccan Education Society was established to impart national education to the natives, and with that motive, Lokmanya Bal Gangadhar Tilak, Vishnu Sastri Chimpurkar, Mahadev Kalyanam Doshi, all these great leaders, they have started Deccan Education Society to impart quality education at affordable cost to the natives. But now, as the time is changing, we cannot restrict only to the national education, but as per the time, as per the need of the era, we have to modify. And accordingly, the Ferguson College, the various units of Deccan Education Society are taking the leading role in all these subjects, then teaching methodology as well as the research work. So, Deccan Education Society is one of the historical education society and very well known college is Ferguson College. And now when Vijnana Bharati is going to conduct any program in Pune, it is of course that they would like to get associated with the Ferguson College. And we really enjoy working together to bring such quality programs to the Puneites and to all the colleges. And today, now with the joint efforts of Vijnana Bharati, Deccan Education Society and Global Indian Scientists and Technocrats Forum, we have organized today the lecture of Professor Ashutosh Kotwal. So I welcome all the dignitaries on the dais, and we will now go ahead with the remaining part of the program. Thank you.
Where people used to teach modern science. Naturally, Dr. Jagdish Chandra Basu had this idea that he will teach science to his country. So he made an application. He was having a letter of appreciation from his guru, Dr. Lord Rayleigh, who was a chairman of Royal Society then in London, and who received Nobel Prize in the year 1904. So Jagdish Chandra Basu carried that letter of appreciation, and that letter was written to Lord Ripon, who was the then Governor General of India. And he further forwarded that letter to the Department of Education in Kolkata. But an officer sitting over there, Alan Croft, he responded to Jagdish Chandra Basu in this manner. This has been recorded in the first biography of Jagdish Chandra Basu, which was written by Sir Patrick Geddes. So Patrick Geddes has described this entire episode in a very unique manner. What Patrick Geddes has given, the description is like this. He said Jagdish Chandra Basu received a response in this manner: Indians have no aptitude for exact methods of science, so no Indian can teach science. So we cannot accept you, being an Indian, as a teacher of science. So that kind of humiliation was there. At that point of time, Britishers divided our education system in two parts. One stream was called as Imperial Education Service, where only British people, white-skinned people, they used to teach anything, any subject, any damn subject. And there was another stream called as Provincial Education Service, where only Indians, they were given chance to teach any kind of stream of knowledge. And what kind of discrimination was there? If an English person is going to get salary of say ₹1,000, then Indian having similar capacity, having similar knowledge, used to get salary of 300 rupees, 2/3 less than that of British person. So it was a racial discrimination, it was a sheer injustice. And Patrick Geddes has described this episode. What Jagdish Chandra Basu did, he has written that Jagdish Chandra Basu initiated a new form of protest against this racial discrimination and sheer injustice. What he did, because after all there was a pressure from upwards, upside, from Lord Ripon, so they were supposed to accept him as a teacher of science, but they accepted him as a temporary teacher of science in the Provincial Education Service. So his salary that was decided was 100 rupees only. Though he studied in their own universities at London and at Cambridge, but he was given that kind of treatment just because he was an Indian. So first teacher of science in India received that kind of humiliating treatment by British rule. So we need to consider those days, that situation, adverse situation in which our own scientists did excel in those days. We need to understand that part also. And S.N. Bose was one of them. He did excellent physics. Even today we remember him, but unfortunate part is, today many of our people, even in the domain of physics, if you ask them, do you know how this name boson has come? Say, they do not know. They simply do not understand this. It is because of S.N. Bose. So here is a time to remember all those great people and why they did that kind of excellent science in those days. Because they wanted to challenge British intellectual hegemony. They wanted to showcase to the entire world that Indians also can do science. Indian can do science even in better way than that of British people. And here are so many examples. So, Dr. S. Chandrasekhar rightly described or responded to that question that there was a need of national expression. Understand these words. There was a need of national expression to showcase British that Indians are equal even in the domain of science. So, let us remember those great people. They were freedom fighters and they carried out struggle for achieving freedom through science, that we need to remember. It is not that they are supposed to go on streets having some placards in their hands and go to jail after doing some satyagraha. Jagdish Chandra Basu did what he did. So he stopped taking any single paisa from British people, but he kept on teaching physics over there without receiving any single paisa, and that not only for 1 month or 2 months or 3 months. He didn't take his salary for continuously 3 years. So in my opinion, that was the first satyagraha in our country against sheer injustice. So I came across a definition of satyagraha. It says, what is satyagraha? It is a determined, non-violent protest or resistance against injustice. So in my opinion, it was Jagdish Chandra Basu, the first scientist in India of Galilean tradition who fought against British intellectual hegemony, and Dr. S.N. Bose was his ardent follower, and he did same thing. With his science, he could challenge British hegemony. That is what we need to remember, and this Azadi Ka Amrit Mahotsav, the celebration which we are doing in the country, gives us an excellent opportunity to understand, explore what our scientists did in those adverse days and how they made science a tool in their hands to carry out struggle against British Raj. So let us remember that this was my responsibility over here. So I stop over here with a request to all of you that let us explore what has happened in the domain of science during the freedom struggle. Namaste.
Thank you very much, Jayendraji. There is one request for all who have come in, that if you have not scanned the QR code at the door, at least while going out, scan that code so that we can have your information. So technology has gone ahead. Earlier we used to take the forms, fill up the forms. On the lines of Sri Jayendraji, the national spirit, now I'll say, अब दिल थाम के बैठिए. Hold your heart, hold your breath, to become witness of an unprecedented unparalleled, groundbreaking work of Professor Ashutosh Kotwal and his team of 400 scientists. Yes, an Indian scientist. A very proud moment of all of us. And I should not say Marathi because there are other people who are also watching. Professor Ashutosh Kotwal is now Fritz London Professor of Physics at Duke University. Yes, he teaches physics till now. In spite of his very busy research schedule and the discoveries that he is making, he is still teaching physics, and that is really a lovable part of his time. I'll briefly introduce him and then we will felicitate him. In fact, he doesn't need an introduction in physics faculty. He is a fellow of American Association for Advancement of Science and American Physical Society. He is recipient of Alfred P. Solon Fundamental Fellowship. He was awarded Junior Investigation Award from Department of Energy. He is a project leader for analysis, software and computing on CDF, that is Collider Detector at Fermilab. He is head of Experimental Particle Physics Research Group at Duke. He received Dean's Leadership Award for Duke University. He was a chair of Duke University IT Advisory Committee and Associate Chair of Physics. Now, one more interesting thing I'll tell about him, particularly physics teachers and scientists, please listen. His citation index is more than 0.2 million. In Indian language, I should say 2,16,860. This is from Google Scholar. Maybe from other databases it will be more. His H index is 219 and I-10 index is 1,276. I'll explain for other people what is that. H index 219 means out of his total publications, 219 publications are such that each is cited by at least more than 219 people. I am also a physics teacher. If my paper is cited by 150 people, I dance. One paper. And most of the papers are in very prestigious journals. What is I-10 index? A paper which is cited by more than 10 people. So 1,276 papers are such that each of these papers is cited by at least 10 research workers. This is the quality and quantity of research he has done. We are very proud of you, sir. To cut short, I now request Dr. Sharad Kunte, Chairman of Deccan Education Society Governing Body and Council, to felicitate Professor Ashutosh Kotwal as a token of our love and respect. On behalf of Ferguson College, Deccan Education Society, we are felicitating Professor Ashutosh Kotwal. We are very lucky to do that, sir. Thank you very much. There are two more organizers of this program, Vigyan Bharati and GIST, Global Indian Scientists and Technocrats Forum. As I said, we have a pool of scientists and technocrats working outside India for India. So this forum and Vigyan Bharati also, the forum is also a part of Vigyan Bharati. They are also organizers of this program. So on behalf of those organizers, I request the National Organizing Secretary Sri Jayendra Sahasrabudhe of Vigyan Bharati to felicitate Professor Ashutosh Kotwal. Thank you, sir. And now the moment for which all of us are waiting. the lecture by Professor Ashutosh Kotwal regarding W boson and his work on that, and Higgs is not enough. The verdict is given by W boson. So I request Sir to start his lecture. Thank you. Sir, you can sit there or if you want here also.
Thank you for all those kind words, and I must say that some of those indices that were quoted, I did not know about them myself. So you can be sure tonight I will go and look up some of those indices and see what the story is there. And most of all, I want to thank all of you. I know it has been raining, and so you all took the trouble to listen to this particular talk. I really appreciate that so many of you have come. So let us get started. The whole story starts with this paper. So, as you know, Science Journal, along with Nature, is one of the two most attractive journals that people would like to publish in. So we decided that other than publishing in particle physics specific journals, this time the particular research here might be of interest to a broader scientific community. So we decided to publish in this journal. If you look in the fine print, it says the W boson mass that we have measured here is more than what is expected. So the purpose here is to understand what is the significance of this statement. What is the expectation? What is the reason that the mass of this particular particle is calculable so precisely? I will also then explain how we measure it this precisely, and the fact that there is a disagreement between the measurement and the particular calculation that is performed in this standard model theory is of some significance. We do not yet know completely how the story will unfold, and I can mention that in the couple of months that this paper has been out, already it has achieved something like 135 citations. So the number of people worldwide thinking about what this could mean is quite a few, and we will see what the conclusion ends up in a few years perhaps. I will also mention that the number of media mentions that this paper got was somehow pretty large. I didn't expect that myself. It got, within a few weeks, something like 830 media mentions. This information was all collected by the press office of the Department of Energy in the US. They are, of course, interested in how the papers that they support, how they are received. And somebody estimated, some algorithm estimated that the total worldwide viewership of all those media mentioned was something like 1.6 billion. So let us see what the story is behind this particular measurement. What is the story behind the expectation? What a particular theory was telling us this number should be, the number appears to be different, and what that might be. On that front, let's start from the beginning. So I will break up the presentation into a number of parts. First, I will start with the history of particle physics. So on that front, particle physics, broadly speaking, means whatever everything is made of. So if you look around and you realize, there are so many different kinds of substances, what are they made of? So this idea is very old. Aristotle himself presented a logic that maybe everything is made up of elements, and he said there are 4 elements. So everything is made up of earth, air, fire, and water. That was some logic. Now we know that the particular things that he mentioned are not exactly the elements that we understand much later, but this was then picked up by chemists. They did a lot of precise measurements, and they realized that certain substances always showed up in a particular ratio. So they understood, okay, everything is made up of molecules. That's the smallest unit that carries chemical properties, and molecules must all be made up of a particular combination of elements, of atoms of this type and atoms of that type.
So the concept of an atom existed as soon as the concept of molecule was understood as being made up of a fixed proportion of things. So those were the elements that atoms consisted of. Other experiments happened, and then people understood that atoms themselves had positive and negative type things in them, so positive and negative charges were understood. Around 1911, there was a groundbreaking experiment. So let's revise the history of this, because perhaps this is the beginning, formally speaking, of particle physics. He had the idea, so his students were conducting this, and they did not understand what it meant, so they brought him in, and he thought very hard about it. He had an idea that let's put a gold foil. By then, radiation was discovered. They did not completely understand what radiation was, but they knew that some point-like radiation, something was coming out of elements. So this is an alpha particle, which we now understand as the nucleus of helium. And he saw, his students and he saw together, that every once in a while, this particle, instead of going straight through the foil, which is what happened most of the time, we have to understand what was the understanding of the atom at that time and why that particular observation was completely revolutionary. So here is the source of radiation, and there is the gold foil. They knew how to visualize radiation. So they had material which we now understand as fluorescent material. So when a high energy radiation hits the material, it emits some light. So this is how TV screens work. Coming from backwards direction. So most of the particles went forward. So we saw this part of the screen being quite bright, but every once in a while we would see some light back here. The significance has to be understood in the context of what was known then. So here is a model. We can call plum pudding model because it looks like a plum pudding. So here is the pudding and here are some plums in it. And the logic was, we know atoms contain positive and negative charges. So based on what we know at the time, and this is the theme that will continue, based on what we know at the time, so here is the logic that positive charges together mixed up in some kind of plum pudding situation wouldn't explain why positive charges and negative charges are attracting to each other. So that when the positively charged alpha particle comes through, it would experience some repulsion from the positive charges. It would experience some attraction from the negative charges. Since the positive and negative are mixed together uniformly, on the whole, you must have no net attraction or repulsion, and therefore all the alpha particles should just plow right through this plum pudding. This is what happens most of the time when Rutherford did his experiment. But in this picture, it is impossible to understand, and so the mathematics was done, how occasionally a particle could bounce back with such a large angle. And the frequency was small but not negligible, so it was quite observable. Immediately, this interpretation analyzed mathematically turns into a completely different model of the atom. Right? So the entire theory has to be revised. This only means that this alpha particle, which is fairly heavy, in order to bounce back at such a large angle, has to be hitting some very, very dense core. So this kind of a mixed plum pudding is not able to reflect back an alpha particle at such a large angle. You can immediately realize, knowing the physics of the time, why this completely changes your understanding of nature. First of all, if all of the positive charge is localized in such a small region, which is the reason why something hits it only occasionally, most of the time you don't hit it so you go through, but when you do, if you have to bounce back like this, it is like a ping pong bouncing off a wall, and that has to mean the mass of this thing is much bigger than the mass of the alpha particle. And so they knew the mass of the alpha particle. So this meant that the positive charge was localized in a very, very, very dense region, very massive. You realize right away why this is not possible with the understanding of the time. A lot of positive charge collected together is inexplicable if you think the positive charge must repel positive charge. So how is all of this positive charge able to stick together in spite of the very large electrical repulsion? They knew about electrical repulsion. which immediately meant that there had to be at least one more force in nature substantially stronger than even the electric repulsion. By figuring out this analysis, they figured out what the size of the atomic nucleus was, and to have that many protons that close together, able to attract each other and stick together, even if there is such a strong electric repulsion between them, had to mean there had to be a force in nature much, much, much stronger than the electric force. So they called it, maybe not so imaginatively, the strong force. Now we understand the strong force much deeper, but it is essentially the reason why the protons are able to stick together in spite of their electric repulsion. So immediately this tells you there is another force in nature which is much stronger than electric. If you have studied electromagnetism, you then also realize these electrons, which are the negative ones circling around, why are they not attracted to the positive charge and therefore collapse into the nucleus? Well, you can do classical mechanics and say, that's okay. We can say that the electrons must be rotating around, and so because they're rotating, they go in a circular path, so they experience an attractive force, but that is the centrifugal force, right? So standard undergraduate physics. But then you study electricity magnetism, which they knew by this time, 1911, and they realized that if electrons are circling around the positive nucleus, that means they are experiencing an attraction, therefore they are experiencing an acceleration, F equals mn. If electric charge accelerates, it must radiate. So this is how they knew they had already detected in 1865 radio waves by accelerating electric charge. So these electrons going around must be emitting radio waves. Now if they emit radio waves, by energy conservation, their energy must reduce, and therefore eventually all their energy will be lost by radio waves. They will circle in and hit the nucleus. In other words, this atom is intrinsically unstable. It cannot exist as defined by the existing laws of physics. And yet here we are, right? We know what the time scale of this atom collapse would be, and the atom is clearly stable, and we have been for billions of years, as we know. So immediately you realize that electricity, magnetism, Newton's laws, all of that has to be completely modified in order for such a simple atom model to actually even exist, and all of us to be around here to be talking about it. This led to the advent of quantum mechanics. So my entire lecture, and why the W boson mass is telling us something significant, is all about what rules of quantum mechanics do we believe at the moment, and is there any particular rule of quantum mechanics or the ingredients that we are putting into the logic somehow insufficient. So that is the theme of this lecture. In quantum mechanics, we understand all particles are actually waves. Right? So the fundamental logic is there is really no such thing as a point-like particle-like thing, like a ping pong ball or a billiard ball or a tennis ball or something like this. It is actually all describable by waves. When you understand the mathematics of waves, you immediately realize what this famous equation is. This is the Heisenberg uncertainty principle, which is saying that for any wave-like description of physical things, the position of the wave and the energy of the wave, or the knowledge of which you have of their position and their energy, is inversely related, and that inverse relationship therefore induces a proportionality constant. If you bring this over here, that proportionality constant is the fundamental unit of quantum effects. So this Planck's constant, so for H is the Planck's constant, and that tells us the size of quantum effects. If you take this relationship and you say, I want to investigate a particular phenomena at a particular distance, 10 to the minus 10 meters or 10 to the minus 15 meters, the size of the atom, size of the nucleus, size of the proton, neutron, and possibly what is inside a proton or a neutron, which we call partons, so go to even smaller size. By this relationship, you must increase the energy of your probe particle, because everything is being governed by quantum mechanics. So this tells you, if you have a particle of 10 electron volts energy, use this relationship, you can investigate the size of the atom, but not anything smaller than that. If you increase the energy by roughly 100,000, you can investigate things of the size of the nucleus, but not smaller. Now you go to a billion electron volts. So an electron volt is roughly, if one electron goes through the voltage of one battery, 1.5 volts, the amount of the energy that the electron would gain by going across the battery voltage is 1 electron volt. So we are using those units. Now we are substantially higher than a billion electron volts. Our beams are roughly 14,000 times, 7,000 times more energetic than that. And that means we can probe way, way inside even the proton. This started happening at some point at the Stanford Linear Accelerator Center, and the point-like particles inside the proton and the neutron, which were later called quarks, those were discovered in this way. Many, many particles were coming about with this high energy. They were eventually all understood in the same way that molecules are made up of atoms, And atoms, all the different kinds of atoms are made up of a few types of particles, protons, electrons, and neutrons, is combined in different ways. All those different particles were understood as being combinations of different quarks. So there was a great simplification and understanding. Here are some people that we know were the creators of quantum mechanics. This is Wolfgang Pauli. He predicted, among many other things, the existence of the neutrino based on the data. Heisenberg principle is named after Heisenberg. Here is Enrico Fermi. For example, the Fermi National Lab, the US National Lab, is named after him. But he did many, many great things, including the first nuclear fission reaction in a sustainable way under the University of Chicago. So this is what is happening in the understanding of quarks. You have a high energy electron beam. This wave here, as everything, is a wave of electromagnetic radiation. In quantum mechanics, it is quantized and it is called the photon. So this photon wave is penetrating because of its high energy and the uncertainty principle deep inside the proton. Inside the proton are these little point-like things or very like little particles called quarks. And so by bouncing off the quark, you are able to tell that the proton is not a single object. It is actually made up of lots of little objects because they are able to sense the little objects inside. Okay? So, coming back to sort of 20th century physics, so many things in our life, it is estimated that roughly 40% of the global economy is now controlled fundamentally by the physics principles of quantum mechanics. I mean, we still build buildings and so on Newton's laws, but many of the materials that go inside our modern infrastructure all have their understanding based on quantum principles of material physics and so on. So here is just a general list of the kinds of things we have seen with quantum mechanics. Okay? Let's move on. The other great foundation is, of course, special relativity. So there is a long story there how Einstein understood a fundamental disconnect between Newton's laws of motion and the laws of electricity and magnetism. And he understood that there was something really fundamental about the laws of electricity and magnetism which was missing from Newton's laws. And that is how we finally understood the impact of special relativity. So now you have two big principles, and of course, what is the next thing you do? You try to make a global theory, an inclusive theory, which includes both the principles of quantum mechanics and the principles of special relativity. So who is the person who first made this attempt? His name should be recognized as much as Einstein's is in some way. I mean, our colleagues, many of the colleagues at the time would admit that. But maybe he was maybe a shy, that is generally how it is said. This is this person called Dirac. Right? So you have heard the name, but perhaps you don't know the impact of his research on all of the development of science. So this is a picture at some conference. I don't know exactly when this happened, maybe 1919 or so. And of all the people you can down there, you can notice, of course, Einstein is visible. Here is Heisenberg, I believe. This, I think, is Wolfgang Pauli. Here is Madame Curie. She got 2 Nobel Prizes. An amazing feat in any century, but certainly back then, for a woman to get 2 Nobel Prizes, not much. No words can describe that. Dirac was the one who initiated this combination of special relativity and quantum mechanics. So anytime such deep principles are unified, it has always been true. For example, when electricity and magnetism were separate principles, but they were combined into one theory of electricity and magnetism by many people, including Maxwell, many fundamental new predictions come about, such as the existence of electromagnetic radiation, such as the existence of radio waves, light waves, and all of that. So this unification also produced a really, really deep understanding of what is matter and what is force. So here is Dirac's understanding, and it is still true, of what an electron is. Let's take something very simple, one fundamental constituent of matter, which is electron. So the electron is visualized as a little bar magnet. So it is spinning, it is a charged particle, it is going around itself. So now you have a current in some sense that is going around. And you all know that a current going around a wire makes a magnetic field. So this electron makes its own little current because of its own little spinning characteristic. And therefore it makes a magnetic field, so the electron has its own magnetic field. Now the electron has a very interesting property, and this is the simplest property you can imagine mathematically of an object that is spinning. There is no simpler description of a spinning object than this particular description. And it turns out that this description gives a very interesting conclusion. If you take an electron and rotate it by 360 degrees, if you take any object around you and rotate it by 360 degrees, you will immediately say it looks exactly the way it looked before. Right? All of us can look around, come back 360 degrees, and it looks exactly like before. However, the simplest description of an object like this, started by Dirac and others, says that An electron rotating 360 degrees around itself becomes the negative of itself. So it's a difficult thing to realize how an object can ever become negative, because it's here, how can it become negative of itself? However, in quantum mechanics, that is not a problem at all, because a wave, on the other hand, every object is a wave, so an electron is a wave as well, and for a wave to become negative of itself is very easy to visualize. Right? So the problem of our conceptual understanding of a negative object is completely eliminated as soon as we realize it's a wave. Any wave that goes up and down like this, if you make a negative of itself, that means that instead of being positive, it is negative, and it has become the negative of itself. Right? So no problem making a negative object in quantum mechanics. There was one other big puzzle, and it was mentioned in important contributions of Bohr, so I will just mention this one, that fundamental particles of the same type, electron or any such object, proton, they are fundamentally indistinguishable. In other words, if you see there's a proton here and there's a proton here, can you actually say meaningfully proton number 1 and proton number 2? I know which one is which. The answer is no. That was not understood until Bose came up with this big realization, and he actually solved many big puzzles in quantum mechanics at the time by making this postulate. And in fact, as was mentioned, his postulate was not accepted, his paper was not accepted until somebody like Einstein said, Bose has hit on the right answer, and immediately got accepted. So it's strange how even other scientists were not accepting of the logic as much as who was saying the logic. And that is not quite the way it should be in science, but such it is. So Bose's logic making electrons indistinguishable, if I can get this simulation to work, I'm not sure why. Let me just give you in 30 seconds what this picture would do if you could run it. If you rotated this coin from there to there, you will realize that the coin has rotated by 360 degrees around itself. So I encourage you to do this for your own, not this way. Right? Try rotating this coin, not moving this one, and you will see when it comes down here, this eagle will be facing up. In other words, it's obvious it has rotated by 360 degrees. What this is saying, there's a beautiful explanation of this by Feynman, so I encourage you to look at Feynman's lecture, that one object rotated like this around the other is the same thing as exchanging the position of this object and this object. Okay? So switching the two coins, one with the other, is the same thing as rotating one coin around the other by 360 degrees. If you try it, you will see immediately it is true. So it's worth thinking about it. This leads to the following conclusion. If you take all the things together, Bose's analysis and this particular analysis, one electron rotating around the other by 360 degrees means, we understand from Dirac, the sign must become negative. So the wave containing two electrons must become the negative of itself when you interchange the two electrons. Right? So this is the two-object wave. This is the two-object wave switching the two electrons with each other. On the other hand, if the two electrons at the same time happen to be in the same place, so two objects same time, same place. Now clearly the Bose logic says you switch the electron with the other electron, but they're exactly in the same place at the same time. There is no way logically you can see any difference. So you must get the same answer as before. So try to reconcile this answer from one logic with this answer from the other logic. Okay? If you think about it for 2 seconds, you're saying there is a quantity describing the two electron structure which is at the same time negative of itself and at the same time equal to itself. So there is the famous number which we think historically came from India, which is 0, and 0 will play a big part in our lecture today. It will show up in this context here that the only object which is both the negative of itself and equal to itself at the same time is the number 0. Therefore, this particular two electron quantity describing the combined effect of the two electrons at the same point, at the same place, is 0. In other words, the meaning of the 0 is the famous Pauli exclusion principle that identical particles like the ones Dirac was explaining cannot be at the same place at the same time. This is the fundamental reason, and the math is so beautiful that it's amazing. In fact, Einstein made this famous quote that the thing that you cannot understand about nature at all is the fact that it is understandable by human beings. He said there is no reason the creation of the universe is understandable by the little thing we call the brain, and yet it is. We can in fact create a logic that explains why matter particles, exactly the way Dirac calculated them, is the reason matter always occupies volume. You cannot compress all matter into the same point at the same time. Okay, so this is Dirac's law. Now let's quickly go to the logic of forces. This is in some easier because this is again fundamental physics from introductory physics. We all know on the surface of the earth, if you try to apply Newton's laws, you invent such forces called Coriolis Force. So you have all heard of Coriolis Force. It is, in some sense, has played an extremely important role in the development of civilization. For example, from Europe, how are ships able to go to America? So what is the wind? You learn in geography, those are called the westerly winds. So why is there a steady wind from that point on the shores of northern Europe towards the shore of America, which is how the ships were able to come? The reason is there is this so-called force coming out, which is called the Coriolis Force, and it is nothing more than the fact that it is not really something pushing the air this way. It is more like the earth is rotating underneath the air the other way. So the rotating frame of reference, which is called a non-inertial frame of reference or accelerated frame of reference, is causing us to interpret the actual motion that occurs as the earth rotates under you as a Coriolis force. Right? So in classical mechanics and undergraduate physics, we call this a fictitious force. This particular idea is now elevated to a logic that says this is not a fictitious force. If you apply this logic consistently in quantum mechanics, then all forces are actually explained by this principle. All we have to imagine is that all particles are effectively in some non-inertial frame of reference, and so whenever they undergo some transformation in that frame of reference, you have to invent the logic of a force manifesting in a particular way, essentially the same thing as why is a hurricane always looking like the air is spinning as it comes to the center. So we know the logic that the air is hot in the middle, so the hot air is rising and the cool air must come in to fill the sort of vacuum. So why is it not just flowing in radially instead of spinning around? The answer is it is coming in radially just as you expect. But it's the earth that is spinning under the air flowing this way, and because you are taking the picture in the earth's frame of reference, it is the air that appears to be spinning the other way. So this is not really the air spinning so much as the earth spinning underneath you and Newton's laws together. So the fact that we will interpret this as Coriolis force is exactly a logic which is taken to the next level and saying all forces are explained by this logic. Effectively, that everything is a non-inertial frame of reference. Okay? So now we take it to the quantum level and say what does quantum mechanics do? It takes all these waves, and every force is a wave, every particle is a wave, and it will convert that to a particle-like picture. So this is the origin of the famous wave-particle duality. The fact that we had a difficult time for a while understanding how something can be a wave and a particle at the same time is actually just, in some sense, a limitation of our rigid mind, shall we say. It is in fact known that if you can imagine a wave which is not spread out over the surface of the ocean, but it is localized in one place. So it has a particle-like characteristic or a particle-like manifestation. How would you imagine a wave that is localized in one place? In fact, you all know it. It is called a tidal wave. So if you watch a video of a tidal wave, you can clearly see it is not a lot of ripples, it is one large crest, and it is coming along at high speed. And the fact that it carries a lot of energy and a lot of momentum and can knock down everything from buildings and trees to everything else in its way is effectively the same as if some massive truck or something was coming along, or a cannonball was coming along and knocking down everything in its path. Right? So a tidal wave and a cannonball really are not very different in all the respects that matter. A wave can reflect just like a ball can reflect. Right? The fact that you look at yourself in a mirror and you see the light reflecting off the mirror is just an electromagnetic wave, light wave reflecting off the mercury at the back of the mirror. So we know waves can reflect, we know waves carry energy, we know they carry momentum, and they can be localized in one spot just like a tidal wave. So in fact, if you think hard about it, you realize a wave can exactly have all the properties that a so-called particle can have, and this is the logic by which in quantum mechanics, the wave nature of everything is in fact converted to a corresponding particle nature, and this is how the quantization is done. So another famous character, Richard Feynman, he would always give a lecture, and every time he drew this particular representation of a particle exchanging a force with another particle, so this is how we think the electron is repelling the electron. What is really happening is a wave of electromagnetism, which is quantized to call the photon. This object is transferring the energy and the momentum from there to there, and this is how the two electrons experience an attractive or a repulsive force, by exchanging a wave or a particle between them. It is said that every time Feynman would explain this to his students at Caltech, every time he drew such a diagram, the rest of the world would call that the Feynman diagram. He would of course just call it the diagram. And famously it is said that he would look back and raise his eyebrows like this, trying to make you realize that the diagram is named after him, so he does not have to name the diagram himself the reflection. But the rest of us call it the Feynman diagram. So this logic has worked beautifully. The quantum theory of electricity magnetism is the most precisely tested theory. Today we will discuss the W boson mass with a precision of 0.01%. This is far, far larger than that, a far higher precision than that. So many aspects of the standard model are tested to various levels of accuracy. It's a measurement-based science, right? So we make postulates, but you have to have experimental proof of them. So this particular logic is extremely well tested. Here is another famous person, Homi Bhabha, electrons, but here is a logic where electrons and positrons can interact with each other. So this is antimatter particle associated with electron, and they have the same kind of Feynman diagrams explaining, just like electron-electron scattering can happen, electron-positron scattering can happen the same way. So this kind of scattering process, which is observed ever since then, has been called Bhabha scattering in the honor of Homi Bhabha. So this logic is now extended to the weak force. So now we start coming closer to the W boson. The W boson is the mediator of the weak nuclear force, just like the photon is the mediator of the electromagnetic force. So here you see a nucleus emitting a beta particle, which was called beta radiation back then, 120 years ago. At some point it started to be understood that what was really happening was one of the neutrons in the nucleus was turning into a proton, and then the neutrino and the electron, the beta particle, were coming out. So this was the particular decay happening inside the nucleus. Then we fast forward some more decades and we realize the neutron and the proton is made up of quarks. So this description was actually more accurately this description, that one of the quarks in the proton and the neutron was turning into a different quark in the proton, and that particular interaction was mediated by the same mediator of the weak force. So hiding inside here is the W boson somewhere, which through this logic to that logic to that logic is explaining how the W boson is mediating the weak decay in the nucleus. The kind of force that you imagine the W boson is representing is exactly the Coriolis force. In other words, the logic here is the same mathematics as imagining a sphere. The neutron and the proton, or in this case electron, neutrino, are the two poles of the sphere. So instead of the Earth rotating, there's some other mathematical description of the sphere rotating. And the transformations that will take you from the south pole to the north, or the north pole to the south. The third type is the transformation that takes you around the equator. If you think about it, those are the three kinds of movements you can do on the surface of a ball. For each of them, there is one of these mediating particles. There is the W minus boson, the W plus boson, and the third one going around the equator is the Z boson. So if you read about the weak interaction explanation, you will see those three kinds of particles associated with that force. And the reason is those are exactly what we imagine as moving up and down or around the equator of a sphere. Okay. So this logic is crucial. So you realize the importance of the weak interaction when you think about the sun. Of course, the sun is crucial for us. Notice what is happening here. This is nuclear fusion. This is hydrogen fusing eventually to become a helium nucleus. But notice here you need two protons and two neutrons. Here you're starting with protons and protons. So fundamentally, the universe was made up of protons and helium. Where is the protons, four protons, how are they turning into the nucleus plus two protons coming out? Somewhere you have to turn some proton into a neutron, somewhere. That is happening right at the beginning. This collision here cannot happen unless a proton turns into a neutron at the same time. Because the two protons are repelling each other, they will never stick together. However, if the proton turns into a neutron, now the neutron and the proton do not repel each other, because one is electrically neutral, the other is charged, but that's okay. But the strong force does not affect that, so the strong force is able to stick them together, and there is no electric repulsion anymore. So this process is crucial. So you ask, how is this process running? How long is the sun going to burn like this? How many years will it continue to burn? Why is it burning at the one specific rate which allows the planets to form and the right amount of energy flux coming out so that the planets not become completely cold, or that the planets just don't completely evaporate away from the energy of the sun? You realize that for the solar system to be stable, this process here has to happen at some specific rate. Too fast is no good and too slow is no good. If you look at the time scales in this chain, you realize that the slowest time scale is exactly the weak interaction time scale, and that is dependent completely on the W boson. So in other words, the time scale in which the rate at which the sun is producing energy is completely determined by the rate of the weak interaction that happens there, which is completely dependent on the mass of the W boson. So in some sense we owe the sun's existence to the mass of the W boson. Here is another thing that we don't realize, but the Earth's core is hot. Now, why is it so important that the Earth's core remain hot? Because otherwise the Earth would become completely inert like the moon. One crucial manifestation of it becoming inert is the electric currents that are happening in the liquid part of the Earth's core, which is iron and nickel. So it is conducting and it is rotating. So that produces a current. That current produces the magnetic field of the Earth. So it's crucial that the Earth have a magnetic field. Because the sun is producing a large flux of charged particles, those charged particles experience a force in the Earth's magnetic field, and so they are deflected away from the equator towards the poles. So you have heard of the northern lights and the southern lights, and that is eventually the charged particles hitting the air near the poles and producing the tube light effect. So that's how you get the northern and southern light. But the reason they are concentrated there and not hitting the equator is because of this magnetic field deflecting up there. So the magnetic field of the Earth is acting like a very important shield. In fact, no life on the surface of the Earth would ever survive the radiation unless the Earth had this magnetic shield. And that magnetic shield is coming about because of the molten core, so it's very important that the Earth's core remain molten. If you now calculate why the Earth's core is still molten after the 4.6 billion years, should have cooled off by now, it is because there are radioactive elements in the mantle of the Earth which have some particular decay chain. So there is uranium decay, thorium, and so on. Very much in the beginning of this decay chain, there is a weak interaction again. So this weak interaction gives a particular lifetime or the rate of decay of the nuclear elements, of the radioactive elements in the Earth's mantle. They are decaying slowly at some rate. That decay is producing nuclear energy. That nuclear energy is helping this Earth remain molten at the core, which is the reason that the magnetic field survives, and that's the reason we survive. So here are a couple of examples we would never realize that radioactivity from the weak decay is actually crucial to not only our existence, but the existence of all life on Earth. And there might be some life that could evolve underground or something, but it wouldn't be anything like the life we know. There is another person I want to acknowledge, which is B.C. George Sudarshan. It has been mentioned that there are so many contributions he made that he should have also won the Nobel Prize, but for some reason or other that is no longer possible now because he actually passed away in 2018. But one of his major contributions, which were made more famous by other people, somehow he didn't talk so much about it himself, is that the particular form of the weak interaction, this weak force that we now understand to be true, was actually postulated by him before anybody else. Right? So he should get the credit, and his advisor, Robert Marshall, should get the credit for understanding how the weak force actually works. Okay, so let me quickly move forward to the one aspect of the W boson, which is the mass, which is not consistent with the theory of forces. This is how you come back to the zero. So the vacuum we again believe is zero, and this will keep coming back again and again. What is the vacuum? We think it is zero, there is nothing there. But in fact, it will turn out over and over again in this lecture that what we call the zero of the vacuum is actually much, much richer and much, much more complicated. There's a lot of physics going on in this zero of the vacuum. The first thing that was done to explain the mass of the W boson was to fill the entire vacuum with this interesting thing called Higgs. So people have talked about the ether for some time ago. Perhaps the ether that people were imagining is actually this Higgs. It's a matter of history. But the fact that we can fill up the whole universe with this Higgs field is the reason that all particles going through this material, in fact, in some sense, experience a kind of friction associated with moving through this vacuum, because it's not a real vacuum. And it's that friction that slows them down and imparts the property of mass. So if you look at special relativity, everything moves at the speed of light because it starts out massless. But then when it slows down, the only way to become consistent with special relativity is to have the mass property. In fact, that is what we mean by the mass property. So here is a caricature of Einstein trying to move quickly, but all these people represent the Higgs field which are sticking to Einstein. So by sticking to him, he is not able to walk fast, and so by slowing down, it appears that he is now a slow-moving object, and that makes us think of Einstein in this case as a massive object. So all massive objects are effectively moving through the Higgs field, which is something like a sticky field. Yes. So here's an analogy of something that is streamlined, so it moves through the water quickly or fast. So that would be a fast-moving particle, and therefore it is a light particle like an a very funny shape, so all it means is it has a large friction, so it is not able to move through water as fast as a fish, so it moves slowly, and that's the origin of a heavy particle. So we have turned the mass of the particle into a friction coefficient effectively with the Higgs field. Right? And ripples in the field are what we call the Higgs boson. This is our understanding of what the Higgs boson is. You have these creating ripples. So let's move on. So we now understand, moving to the 100 years moving forward, what is the standard model or standard theory. It is taking this description of matter particles and replicating it so many times. So here is our friend the electron, but is now replicated for the neutrino and the quarks, and there are 6 types of quarks and 6 types of these particles. So we now have a total of 12 matter particles which explain all the matter content of the universe that we know about. It does not explain dark matter. It's crucial that we recognize at this point there is no room for dark matter in this picture. Here is our theory of forces, we talked about it. Notice the elegance of the equation. So all interactions of matter with energy are, and the propagation of the energy itself, like electromagnetic radiation. The number of phenomena that you can imagine that are encapsulated in this one tiny equation is just amazing. So in some sense, this rightly called the crowning achievement that we have a theory which incorporates so much knowledge and so much understanding that an equation that you can write down on one line, really 7 or 8 characters, describes essentially all matter, all energy, and the interaction of matter with energy. Now we turn back to the vacuum. So here is coming back to the importance of the W boson. The vacuum is not zero in another major context. It is something that is best described as a quantum foam. What does that mean? We come back to the famous uncertainty principle, and we say that this is the amount of energy that you cannot know how much energy you have any more than this. So it's an uncertainty. It's a level of ignorance on the level of energy that you actually have. If you have a level of ignorance like this, which is inversely proportional to the amount of time, it is like a bank. So imagine you go to a bank and you say, I want a loan, and they will say, how much collateral do you have? We will give you as much loan as you have collateral. So there is some kind of conservation going on. That you cannot borrow $1 million or $1 million rupees if you only have $1 to your name. They will not give it to you. On the other hand, nature itself acts like the kind of bank that we would all like. It will give us as much loan as you like. You can have $1 million or $1 billion or $1 trillion. That's this number. As long as you say the time for which the loan is valid is inversely proportional with the proportionality constant being the Planck's constant. In other words, if you want $1 million loan, the bank will say you can have it for 1 second. If you want $1 trillion loan, sure, they will say have it. But you can have it for only 1 millisecond. By that time, you have to give it back. If you want $1 trillion, just keep going by every factor of 1,000, and they will say you can have that loan for a microsecond. What this means is nature is able to exploit this type of bank and say, if I want to create new particles, I can have as much energy as I like to just pop them from zero, from nothing at all. I can create all the particles I want. So the vacuum is in fact constantly manifesting every particle and every force that is present in nature. We may not know about it, but nature of course knows itself completely. So it will manifest all of these particles constantly, no matter how heavy they are. So you say, where does the energy come from to create this particle? The answer is the uncertainty principle. If the particle is very, very heavy, so you need a lot of energy to create it, that's fine. As long as you create it for a time which is very, very short, consistent with the uncertainty principle. So the bubbles are popping in and out in the vacuum all the time. The higher the mass particle you want to create, or nature wants to create, it can pop up, but it must disappear within the corresponding amount of time calculated by the equation. Okay? So everything that can happen at extreme high energies is actually constantly happening in the vacuum around us all the time at every point in space. But you will never realize it because by the time you go and say, oh, but that particle is there, how can it be there? There is no energy to create it, that cannot happen. It will disappear before you can spot it because the time associated with that fluctuation is tiny. And you will not be able to measure that particle in direct, so you can never prove that this bank exists because the particles are created and they disappear before we can actually sense them. So we will never be able to tell directly that this vacuum right here is constantly bubbling like a foam, which is boiling and disappearing, boiling and disappearing. So here is an animation of that. Every point in space is, watch any point here, and there is a bubble that appears, and before you can spot it, it disappears. the bubble can have infinite energy in principle according to quantum mechanics, as long as it disappears in an infinitesimally small amount of time. So how do we know about the existence of these bubbles? I mean, is this all science fiction, or is this a real movie which we have created consistent with the properties of quantum mechanics? So here is the alternative title of my talk. This is nothing. He is referring to the vacuum, but all of the things we are going to talk about today in the remaining time are related to this particular property of the vacuum. This is in fact a demonstrated principle. So if you go back to 1955, Willis Lamb wanted to see if he could sense these so-called vacuum fluctuations. He found these particular states of the hydrogen atom, they were calculated at that time. Their energy difference was exactly known by the principles known at that time. What he did a very clever measurement of the difference in the energy levels of these two states. What number did he get? He got almost the number that was expected. So what do I mean by almost? What he measured was 1 part per million. So 5 decimal places and then 1. 1 part per million difference in what he measured compared to what was calculated as the energy of these two states, the difference of those two states. They should have had the same energy according to the calculation, which did not include the vacuum fluctuations. At that time, vacuum fluctuation calculations were not that well developed. Some time goes by, we have a lot of brilliant people, you will recognize these names, you will find them there. They started working out a quantum theory of electricity, magnetism, their interaction with the electric field and so on. And they started working, we see 10 years later, that this process, the electron experiencing a force from the proton, we call this is hydrogen, just a proton, that this force, which was using this particular calculation alone, 1 photon being exchanged, tells us the energy of these two states must be identical. But you must now include the vacuum fluctuations. So notice this photon is fluctuating into an electron-positron pair. The photon does not have the energy to create this for real, but the vacuum can borrow energy as much as it needs, create the little bubble, and before you can spot it, the bubble disappears. So this is what is illustrated here. The bubble appears and disappears. So according to this electron and this proton, there is just a photon, but that photon is experiencing the quantum fluctuations in the vacuum. These people started working out this logic, and they found that by this calculation, they could exactly explain this 1 part per million difference that Willis Lamb had measured. So he had already received the Nobel Prize, but for explaining this logic, they were also able to get the Nobel Prize on many other things that they did. But this was the first experimental proof that this quantum mechanical prediction, that the vacuum itself is so rich that it is bubbling all the time, and you can sense the fact that the bubbles exist even if you cannot detect the bubbles directly. This is the principle on which the paper we are about to discuss is becoming relevant, or why is it making a significant statement. The W boson in a word is also able to experience such vacuum fluctuations. Whatever particles might exist in nature, we may not know about them, but nature will manifest them in these bubbles, and there are observable effects that these bubbles have. Even though you cannot detect the bubble directly, they will have an observable effect, such as this small energy difference, 1 part per million, that was observed by Willis Lamb. Okay? I showed this picture before, and you noticed that there were other little wiggles between the quarks inside the proton. So what is this? This is the theory of the strong interaction, again explained by the principles we talked about earlier. So there is the strong force being mediated between the quarks, and that is why the quarks are sticking inside the proton, and that is also why a proton is able to stick to the neutron and so on. So the existence of the proton, the existence of the nucleus is also owed to this strong force. There are those bubbles again. So here is a wave of the strong force creating a bubble. Here is another kind of bubble. All of these bubbles have real effects. You can calculate the fact that the strength of the strong force is actually influenced by the existence of these bubbles. So here is a measurement, without going into too much detail, I will show you. This is a measurement of the strength of this force, and you can see that that strength is changing in a very, very measurable way. The changing of the strength is exactly because of the existence of these bubbles, again being experienced by the strong force. So this was a measurement that was made after the prediction. So just like the prediction was made for the photon vacuum fluctuation, a similar prediction was made for the strong force experiencing the same vacuum fluctuation, and that prediction has been borne out. It was in fact a very, very important prediction in understanding the strong force me quickly show you the relevance of these vacuum fluctuations in one more way. Again, explaining exactly how we happen to be here in the first place. It is the notion of dark matter, how galaxies are formed, and the extremely important role played again by the quantum core. So this lecture is not so much about dark matter per se, so I'll go very quickly through this dark matter logic. We know there is about 4 times as much dark matter as proton, electron, neutron, all this kind of stuff. And here is a typical galaxy, and there's a large halo of dark matter around every galaxy. It's the gravitational force which is attracting all of this together. If you look at the distribution of galaxies, so this is actually a slice of the universe, so we are now looking at the entire universe. If you look at the distribution of galaxies spread out in the universe, they are not in fact uniformly distributed. This does not look uniform at all. They are distributed along these filament-like regions with a lot of void in the middle where there are no galaxies. So what would cause the universe to form in a strange way if galaxies isolated or localized to filament-like regions? How do we know this? First of all, we have a very quick explanation of how do we even know that all of these galaxies are distributed in the same way that the dark matter is distributed. So the green is the dark matter, the little orange spots are the galaxies. So you notice that the galaxies are distributed in the same regions as the dark matter is distributed. So there is some common cause to both of them. You could ask the question, if it is dark, how do we even know the dark matter is like this? How can you tell somewhere out there if dark matter even exists? This comes back to Einstein. So Einstein's explanation of gravity is, imagine some sheet of rubber, and if you put some heavy ball in the middle, it bends the sheet of rubber. So now if you were walking along that sheet, you might think you're walking along a straight line, but that's a straight line before the sheet was deformed. Now the force of gravity is essentially the deformation of this fabric. And so when you're walking along so-called straight line, you will actually bend as the sheet is bending because of the depression in the middle. So the bending of the space-time sheet is what is being interpreted as gravity. That is his description of gravity, which is exactly right. This makes a very important prediction that if light were to travel near this star, it will actually feel the gravitational force. So this is not consistent with Newtonian gravity, but Einstein explains it. That it will also experience the bending of space, so it acts like a lens. In other words, all masses of the universe are acting like gravitational lenses, and in that lens, even light is going to bend, like everything else, because we all move in space-time. So it is the gravitational lensing which is measured very precisely, again we come back to precision, and that tells us that even if you don't see a galaxy, it is the bending of the space by the dark matter which you are seeing through the lensing effect. So in fact, you can do that calculation very accurately, and you can tell what the dark matter is. This is how we tell the dark matter. In fact, dark matter galaxies have also been discovered close to the Milky Way. They are 90% dark matter. They are almost invisible, but you can tell they are there. Here is this pattern again of galaxy distribution. You can see very non-uniform. They are lining up along these filament-like regions. So what in the beginning of the universe, at the time of the Big Bang, would explain why the distribution of dark matter and the distribution of everything would follow such filament-like regions. Okay? Now, whenever we take a bath, we take soap and we start making a lather out of it, and you might realize that if you look closely at the foam that you create from the soap, wherever there is a high-density region where bubbles are intersecting, and inside there is air, so there is no soap there, you will notice that this looks exactly like a foam. So in fact, this is some kind of frozen foam. So what is it? We all know about the cosmic microwave background radiation. I'm going to very quickly go through this. It was measured in 1964. It's a radio wave radiation coming from all points in the sky completely uniformly. Turns out it is now understood, and therefore a Nobel Prize in discovery, as an echo coming back from the Big Bang. So at the time of the Big Bang, that big explosion in some sense caused a radio wave coming from a tiny, tiny region, because the whole universe was extremely small. So it was uniform over there, and now that this balloon stretches out and becomes our massive universe, that radio emission was stretched out at the same time completely uniformly, and that is why this is sort of a very strong indication that the Big Bang did occur. This radio wave is all over the universe, same intensity everywhere. Another Nobel Prize came up, coming back to precision. Somebody came along and said, let's measure this radio wave across the sky, this cosmic echo from the Big Bang, more and more precisely. Notice satellite, and that measurement was made even more precise. So what are these tiny, tiny differences in this completely almost uniform radio wave at 1 part per 100,000? The explanation turns out that as the Big Bang occurred, there were of course quantum fluctuations, vacuum fluctuations happening now, happening then. Physics is independent of time and space. So the same quantum fluctuations that happened in the beginning of the universe. The one thing that is different then versus now is now these vacuum fluctuations have to disappear consistent with the conservative principle because there is no real energy present to manifest those particles. So therefore the energy has to go back according to the observed principle. At the time of the Big Bang, however, there was a huge amount of energy available. Right? The universe was expanding. Let's not discuss where the energy came from, but the Big Bang itself in some sense is an infinite source of energy. So the fluctuations that happened back then, instead of having to disappear because the energy is not really there, so you have to give the money back, so to speak, to the bank. In this case, you did not have to give the money back. The universe was generating its own energy, and these quantum fluctuations in fact became real fluctuations. They did get frozen in space, and those small density fluctuations became these fluctuations in the gravitational attraction. And those fluctuations then started pulling on the dark matter, where the high density regions were. So this is how the dark matter formed the filament-like regions around the quantum fold, and that attracted the visible matter, and that created the galaxies and the stars and all of this. So many other things are of course responsible, but the vacuum fluctuations at the time of the Big Bang, these quantum fluctuations, are in fact also responsible, among other things, for the existence of galaxies, stars, and planets, and everything else that is there. This picture is illustrating that the vacuum fluctuations did get frozen back then, and that led to the formation. The entire structure of the universe that we see now, in some sense, owes not only the existence of dark matter, but the existence of this quantum fluctuation. Finally, what does all of this have to do with the W boson mass? Just like that photon, we saw Willis Lamb's experiment, the photon was having quantum fluctuations with electrons and so on. Here are the other particles present in the standard model. We know there's a very heavy particle of matter called the top quark. Without going into those details, the W boson is experiencing all the possible quantum fluctuations that exist in nature. Not only the ones we know about, but all the others that we don't even know about yet. So we can start calculating. Let's calculate this quantum fluctuation. You get a number. Let's calculate the quantum fluctuation with the next particle we have recently discovered, the Higgs boson. So here is some picture of the quantum fluctuation associated with W. You can make this calculation and ask, is the measurement of the W boson mass, which is affected by all these quantum fluctuations, just like the Willis Lamb experiment. When you calculate all these quantum fluctuations, you get a number. I'll show you the number on the next page. Here is the number. Very precise number. You can see the small, the level of precision here is much, much smaller than the actual value. Now you can ask the question, do we get a measurement agreeing with this number or not? The same logic as Willis Lamb. Why might you not get the same number? Well, how do we know that the fluctuations experienced by the W boson are limited to the ones we know about? If the story ends at the Higgs boson, you will say, well, we found all the particles that are present in nature. So these calculations which present this number is the number we should measure. On the other hand, if other particles, like dark matter particles and many other possibilities, I like the dark matter hypothesis myself, were to be present, they would also interact with the W boson and they would create more fluctuations. So you can make a calculation of these and you can add those effects to these calculations that we have already done. So everything to the left here we call the standard model theory calculation. And here is another calculation, for example, adding dark matter to the standard model or adding some other ingredient to the standard model. Let's just call it X for now. So is the measurement more consistent including X, or is it more consistent just including this? And this is exactly like the Willis Lamb logic. Do you add additional ingredients or do you keep your old ingredients? And you might know the famous theory called supersymmetry, so that also adds more particles. If nature they manifest those, we may not know about it yet, they will also create these quantum fluctuations and they will also affect the mass of the W boson. So these can also be calculated. And this one, for many reasons, is quite popular amongst theoretical physicists. But for me, for example, and many others like me, the fact that in the supersymmetric logic, a particle that can have exactly the same properties as dark matter particles, such particles are actually present in this theory. So among many other predictions, supersymmetric theory can make a prediction for dark matter. The standard model has no room for dark matter. So this is another attraction for the supersymmetric. So now we look at it this way. So a plot like this is the first figure in our paper. What is shown is on the x-axis the mass of this top core, which I didn't discuss too much. But the relevance of it is you pick a number here, you get a particular value of this quantum fluctuation. You can go up and say for a particular Higgs boson mass, the other fluctuation, for a particular top core mass, one contribution, you will get a prediction for the W boson mass. In other words, pick a line in this plot for a particular Higgs mass like this, pick a vertical axis for a top core like this. Wherever they intersect, you get a point. At that point, either the W boson mass is there or it's not there. If it is there, the Higgs is enough. If it is not there, the Higgs is not enough. So you see the title of my talk. After 2012, all these possibilities, Higgs mass could have been different numbers before 2012, before its discovery. So different W boson masses were calculated. If you incorporated supersymmetry, then you get other calculations for the W boson mass. So the answer could be there, the answer could be here. If the Higgs boson is all there is beyond what you already know, then the answer must lie on this line. So this is the standard model calculation for a particular Higgs mass that we know, for a particular top quark mass that we know, the answer is either on the purple line or it's not. Back in 1998 when I started in this business, something around 95, so spent about 27 years on this. This was the state of affairs. The blue circle was telling us what was the accuracy with which you knew the mass of the W boson. So in the vertical direction, the answer could have been anywhere from there to there. And this is how we do our physics business. Do we know that the answer is more consistent with the supersymmetric theory or more consistent with the standard model? In other words, is the answer in the green region or the red region? We don't know, because the experimental answer, the truth, is anywhere between there and there, so all possibilities are alive, and you must continue your research. This is what has happened in this paper. The measurement we have published is lying in this yellow or orange circle. So now you say, is this circle lying in the green region, for example? Maybe. It is definitely not lying on the purple line. Right? So the significance of this paper is, in a statistical sense, the consistency of this measurement there with that purple line is less than 1 part per billion. In other words, the random chance that something happened and you got an answer there, but the answer was supposed to be on the purple line, that chance by random statistical fluctuation is less than a part in a billion, is the statement of our paper. So that's how it's physically represented. Let me, in maybe very few words now, say something about how the actual measurement is made, but I have sort of focused on describing what the implications might be, because we are certainly not lying on that purple line. So some other quantum fluctuation is present. What we cannot tell is whether it's because of a supersymmetric particle, whether it's because of a dark matter particle, whether it's because of perhaps the Higgs boson is not alone. Many ideas that the Higgs boson need not be unique. There could be other particles exactly like the Higgs boson. In fact, it could be a pair of cousins, for example, and you have in 2012 just discovered the first one, but maybe there's a second one, maybe there's a third one. Such ideas are also present with good motivation. So, all of those possibilities can produce the effect that we have seen. We just don't know which of those is the actual explanation, but the statement at the moment is we need some additional explanation. All we know at this point is if you only incorporate the top quark and the Higgs boson and everything else we know, the answer should have been on this purple line and it's not. So let's see where this evolves. In a few words, here is a W boson that is decaying. I'm going to skip over some of the details, maybe in Q&A you can ask me. There is a lot of other radiation accompanying the production of the W boson. As we said, it decays to an electron, for example, and this invisible particle called the neutrino. So now you say by E equals mc squared, if I could measure the energy of this particle there, the electron, if I could measure the energy of the neutrino, which I can't, but if I could, then by E equals mc squared, I will know the M of the W. Right? So m of the W is resulting in the E energy of the two decaying particles. The whole trouble why it takes years and years and years and decades is you are not able to measure the energy of the neutrino. So half of the equation that you would put together in E equals mc squared is missing. Now what do you do to infer the mass of the W boson given only half the information that you need and the other half is missing because the neutrino is not detectable. So all of the complications in this measurement come about essentially because of this. So our detectors are effectively large cylinders. These are all layers of sensors. Each of these sensors is responsible for detecting one or two kinds of particles, and you put the entire image together and you are able to see what actually happened. So I want to give an acknowledgement to my colleagues. It was mentioned, like 400, sometimes even more people. So many people working day and night, literally for 20 years, to build this apparatus, which is as high as a 3-story building. Here. And not only building it, but literally operating it day and night. So when it is running, it is really running 24/7 for 9 to 10 months at a time, and then you get a break, and then again running 24/7. And somebody has to be watching to make sure everything is working. And because of this, we are able to do this. Here is another picture of this particular detector. I will quickly just flash through the schematic of this apparatus, which is supposed to install. Here is a very nice picture of a particular kind of detector called the drift chamber. These wires, you see gold-plated tungsten wires, are very thin. They're about 30 microns thickness, so about 1/3 the thickness of a human hair. And they're very long, 3 meters long. So imagine something that thin that has to work like this for 10, 15 years. On top of that, they are present at high voltage. So what happens is a charged particle comes through, it ionizes the gas, so electrons start drifting in the gas. They are attracted by the high voltage. So when a particular wire receives that charge, you are able to say the particle you are looking for went close to that wire. So there are 30,000 wires here. Some fraction of them will give you an electrical signal because some charged particle went through them. And that's how this particular drift chamber thing works. So a quick picture, this was the Nobel Prize winning apparatus was invented by George Sharpak in 1964 and 1962. It has been the mainstay of particle physics for this long. The other aspect is the usual charged particle in the magnetic field. So here is the magnetic field going into the page, and the charged particle therefore goes in a circle because, as you know, a magnetic force is always perpendicular to the speed. So if the speed happens to be that way, the force on the magnetic field is this way, and because they are perpendicular, you can calculate easily by Newton's law, you will get a circular trajectory. So as a charged particle is produced, you are trying to see what circular trajectory is made. By measuring the radius of that circle, you are able to infer what the energy of the particle is. So this is what a typical event looks like. This is the W boson actually producing the data. It's an electronic display, but each of those points is one of those wires recording a charge. If you look very closely, sometimes you're able to tell by eye that there is a particular trajectory that you can draw in circle through. But of course, by eye, when there are 50 to 100 particles produced, your eye is not good enough. Now you need a very sophisticated computer program, which I worked on to find all those little circles. So every one of those circles is an inferred trajectory of a charged particle, and by seeing what the radius of that circle is, you can infer its energy and its direction and so forth. So here is the electron coming from the W boson decay that is happening there. I'm going to skip some of these details, but just tell you that one thing that matters very, very importantly is how well you can measure the radius of that circle, which tells you how well you can infer the energy, which tells you how well you can infer the mass of the W boson. So our research is full of such, knowing all the little steps of all the little inferences that you have to make, and those inferences all have to have a certain accuracy, and that leads you to the final accuracy of 0.01%. So, for example, how well do you know the positions of those wires? We were able to conclude from some analysis I published here that finally we know the positions of every one of those 30,000 wires to an accuracy of 1 micron. So again, I mentioned human hair thickness is 100 microns, this is about 100 of that. So that leads to a particular accuracy on the measurement of the energy. Now we can say, do we know the masses of the other particles before we get to the W? So here is a particular particle, I won't go into the details. What is shown here is the way of inferring the mass of a known particle. It's called the epsilon, which is not shown here very nicely. Its mass is already known, so other people have measured it. We can also measure it with an accuracy of 25 parts per million. So we are not quite at the very slam level. It's not quite 1 part per million, but it's somehow in a factor of 10 of that now. So by showing that we can measure the masses of known particles, so here is our measurement of a particular particle called the Z boson. I mentioned it earlier. The measurement we get is within this accuracy. You can see it's quite consistent within that accuracy. So this is one of the demonstrations we are doing to show that before we get to the mass of the W boson, for the world to believe that we are confident in an accuracy, we are going to measure the masses of other particles whose masses are already known. Are we able to independently reproduce that number before we get to the W? The answer is yes. I will mention that we've done this, so my emphasis has been to do this every single time. So this is my 5th time now. And every time we have used this technique. And of course there is a scientific debate about how do you show your accuracy is as good as you say and so forth. All the other experiments that have attempted this measurement, nobody has actually made this demonstration. But we have always insisted that we will make this demonstration before we get to the W. So this gives us some confidence in what we're doing. So to wrap things up, here is the distribution of energy now coming from the W. And you can see that the distribution is not the same if the mass of the W was one number or a different number. So as the number changes, this observable quantity is changing. So now we have to do a careful statistical analysis. We use our data, we compare it to every one of these predictions in a good statistical way, and the power of statistics is quite strong. It is able to say with pretty high precision that the data are most consistent with one distribution or the other. So this is our final method. I show you for illustration only 2, but in practice we are actually making thousands and thousands of these calculations. So for every possible mass of the W boson, the technique is make a precise calculation of this distribution, then do a statistical comparison with the data, and you get an answer. The most likely one is the mass that you pick. So this is what is happening here. The red line is one of those precise calculations. The blue points are the data, and the chi-square or chi-square probability, learn some statistics, that these are called goodness of fit measures. So it is showing the consistency of the data with one particular calculation, and that's the most consistent calculation. We of course know which W boson mass was assumed to make that particular red capital. And that's the measured value, of course, and how the inference is done. So we are back at this picture, and the end of that long analysis, which I'm summarizing in a couple of slides, but you see the paper itself has something like 50 pages, and a lot of the detail are in previous papers as well. So this is where we end up. So a few words to wrap up. A lot of people, of course, are reading. This is slightly over. In 7 weeks, we have 130 people exploring the possibilities. Could it be supersymmetry that explains this? Could it be the presence of additional rings? Could it be the presence of a dark matter particle, which the W boson is sensing through those vacuum fluctuations? This particular chart was made earlier, so it's 62 different papers have been summarized. And I couldn't do this, so another theory friend of mine is sort of classifying the different types of ideas. For example, the existence of another force, or the existence of new types of matter, or the existence of supersymmetric particles you see here. So this is 3 weeks. Already in 3 weeks there were 62 different ideas being proposed. I am not going to go in the interest of time unless you have question after session. There is a big puzzle, but let me just end here, about a third puzzle that standard model is not able to explain, which is why there is more matter than antimatter in the universe. So Sakharov, the famous scientist and a peace dissident in the Soviet Union in the 60s, he explored this, and he made one, among many things, one important conclusion, that as the standard model exists today, the amount of matter and antimatter in the universe should be almost equal. But we know that cannot be true, because then the amount of matter that is there today cannot exist, because the matter and antimatter would annihilate and turn back into energy. So there would be not enough protons, not enough electrons, and therefore not enough galaxies, and not enough stars, and not enough planets, and not enough us. So for us to exist, one of the crucial Sakharov conditions that is not satisfied by the standard model is in fact satisfied by invoking that the Higgs is not alone. So we are back to my theme, the Higgs is not enough. What if the Higgs was part of a partnership? So there was a second Higgs-like particle present in nature, and we just discovered the first one so far. If the calculations of the Big Bang included the existence of a second partner to the Higgs, then a very important condition from Sakharov, which everybody agrees with, that condition is necessary, which is not satisfied by the standard model, can in fact be satisfied quite easily if such a particle were to exist. So, you can ask the question, is the new measurement of the W boson mass consistent with the vacuum fluctuations, not only of the Higgs, but of the second Higgs-like partner? It doesn't have to be just one, but for simplicity we take one. And the answer comes out yes. So, possibly it is true that what the W boson is sensing is the second Higgs-like particle through those quantum fluctuations. And people have calculated that the disagreement of the W boson mass as measured with the standard model can exactly be explained if such a new particle were to exist. So, why did I pick this one to illustrate? Because it satisfies a crucial Sakharov condition which explains why there is an excess of matter in the universe, again explaining the very reason that it happened to exist. Okay. So on that front, let me not read this entire summary, but you can see why the conclusion happens to be that the Higgs boson does not look like the end of the story. And there could be many more things to come, and I'd like to give you a flavor of how many other possibilities, new possibilities, and what is the motivation for some of those possibilities. What is the motivation that dark matters are particles? We know dark matter exists. What is the motivation for a second Higgs-like boson to exist? Any of those, or potentially more than one of those, is the explanation why this number that is calculated is not the same as the number that we measure. So you can see a very large difference. And in statistical terms, it is called 7 sigma. Essentially, you are taking the difference and dividing by the level of knowledge you have on that difference. So the difference is 7 times larger than how well you know those numbers. And in scientific world, anything bigger than 5 sigma is considered a scientific discovery, and this is more than that. So that is why I think we have the conclusion that Higgs is not doing this. So, thank you for your attention. I appreciate the fact you have stayed this late and listened to this story. I might leave you with this characterization that, when you're looking for treasure, which is how we think of fundamental science, we don't know what good the treasure is. After all, what good does diamond actually do to us except we look at it and admire it? Doesn't feed us, doesn't close us, it's just a nice, beautiful thing to admire. So in that sense, so far we think of fundamental science as something like a sunrise or a sunset. You watch it for reasons that we don't really know. Right? The day will go on the way it was going to go on, whether we looked at the sunrise or not, and yet we go and admire the sunrise for some reason. So, in that sense, whatever that treasure is, historically we said X max is what. So maybe I will leave you with this thought that in the future perhaps we will say that W max is what. And on that note, thank you again very much, and I'm happy to take questions.
Really deserves a standing ovation. Really great. What should I say? Stunned, overwhelmed, delight, many questions in our mind. You answered many of them, but then created new more. So it's the science as you showed there. Every time a new discovery comes, we feel that it's the end of science now. Everything is explained. The next day, a door gets opened and you get a question. 10 years back, 10 years ago, sir, you did one measurement of mass of W boson. It was a very accurate mass determined by you, W boson, Z boson, and that predicted the mass of Higgs boson. The discovery was possible only because of that. So you were the cause of discovery of Higgs boson. So you were the person who said yes, standard model is correct. And now after 10 years, you are challenging the standard model, sir. To mean it, I have to mean the Yes, this is the science. So many things you explained, astonishing things is 1,000 billion collisions. Can you imagine? And you took out 4.2 million W bosons out of that. And you measured. And what is the accuracy level?
That I discussed, 12 different matter particles, and the 3 different forces, the strong force, weak force, nuclear force, and electromagnetic force. I will leave gravity out because typically unification of the 4 forces is a different question. The unification of the 3 forces which have a quantum explanation is the first unification people generally talk about. Perhaps string theory is that quantum theory, but we do not know. That problem is a very difficult problem at a very fundamental level between the features of gravity theory and the features of the quantum theory. So the problem lies that quantum mechanics obeys the uncertainty principle, and the uncertainty principle has fundamentally got a conflict with the gravity logic. And so that's why that unification is so difficult. Perhaps string theory has it right. So let's leave that unification aside. The other unifications of matter, particles together, energy, force concepts together as a single force, and in fact matter and force unification, which are 2 completely separate things for now. One is fermions, one is bosons. That unification. This is called grand unification. This is the unification of everything that is described by the standard model of quantum theory. That particular unification has been shown to be achieved by, for example, supersymmetry. I don't think that's the only answer. There are many other mechanisms that can be invoked. Each of those mechanisms will automatically predict additional particles, additional forces, additional interactions. They always do, just like every other unification in the past has done. Right? Like quantum mechanics and special relativity unified predicted antimatter. There are so many examples of this. So the answer to your question becomes, is any of those additional mechanisms invoked by the unification logic sensible, or is it detectable by the W boson mass that I just mentioned? Many of those, the answer is yes. So all those unification mechanisms predict additional forces, they predict additional particles. Almost all of them participate in the vacuum fluctuations, which this is sensing. So many of those ideas receive support from the fact that this disagreement exists, which is therefore saying those additional mechanisms might be present. We cannot distinguish between them, but those options are now available on the table. Before, if everything was consistent with the standard model, which does not include those logics, then clearly you say those additional logics must produce an additional effect, but we are not seeing that effect, so the additional logics must be excluded. Now those additional logics are allowed. I don't know which one, but they are allowed. So this is a step towards unification. The second one, I did not quite hear, nuclear desert.
Hazard. Like the one that occurred in, for example,
Hazard.
Chernobyl. Yes. Like
Oh, nuclear hazard.
Yes.
Now, see, the significance here is you have a calculated logic containing certain ingredients, and your nature answer is different, which is telling you that your ingredients are not enough. That is what it is saying. But the nuclear hazard that is present in nature already knows itself. Right? The fact of the W boson that is really there is already present in the radioactive decay, it's already present in the uranium plutonium. So the hazard present in nature is not affected by our knowledge of the mass. Nature already knows what the true mass is, and all the radioactivity that is happening and the fact that the hazard creates a problem for us is already a fact of nature which is not in question. What is in question is our explanation of the fact correct or not? That is the question we have resolved. So in this sense, we cannot fix the nuclear hazard. We just have to, like any waste, control the amount of waste you generate and throw it away properly.
Hello sir, I am from Wellington College, Sangli. There are many students watching you live here. So some of the questions from students. So W boson, the first question is, the W boson is a carrier of nuclear force. Now because of the mass is found to be different, the range of nuclear interaction must be different. How will this affect the present knowledge of nuclear physics? And second one is, why we cannot measure energy of neutron decay by W boson?
So your first question. It is similar to the answer I gave earlier. The measurements that are made of weak interactions are a combination of different things. So what is the rate of nuclear decay depends on what? So I mentioned it depends on the mass of the W boson, but that's not the only thing. It depends on the interaction strength of the W boson with the proton and the neutron and so on. So it's the mass and the interaction strength together is what is involved in that calculation. So if the mass is slightly different, to us it means that therefore the interaction strength is a little different from what we thought. So it's the entire logical interconnectivity of this principle here and this principle there and this principle there. Are they all self-consistent and agreeing with all the different experimental measurements? So it's only when you combine all the data that you find that those measurements are all consistent with one answer, but some other answer is inconsistent, and therefore an additional ingredient is required there. Right? So it's a sort of multi-step logic. If you take any one experimental observable, like nuclear decay, then a particular set of combination of concepts together explains the nuclear decay. If you change one of those concepts, like this is saying, then the other concept has to change accordingly, and you can still get the right answer. Right? So, in other words, when you have three unknowns with basic algebra, right? We all know how to solve linear equations. If you have a linear equation with three unknowns and you have one observable, all you get is a connection between the three, but you cannot solve for all three. In other words, if one of them changes, the other two can change, and the equation still works. So, we explain the example that I am giving twice is, how does any one phenomena get affected? And my answer is, any one phenomena is like writing down one equation with three unknown variables in it. If I tell you the answer for one unknown variable is different from the others, that doesn't mean that one equation is broken, because it just means the other two variables have adjusted. Standard linear algebra. What we are finding here in the inconsistency is the same as linear algebra. When you have multiple equations from multiple observables, and you try to say I can explain all those equations with the same 6 unknowns. Now either the equations are exactly solved or they are not. In other words, do the 6 lines intersect at one point in 6-dimensional space, or they don't? This is saying the 6 lines that you have observed so far are not all consistent with a single intersection point. That's the sort of analogy. But no single equation, you say, is that equation the wrong one, or is that equation the wrong one? We cannot yet tell which equation is the wrong one. We are just saying the 6 equations together, which is the standard model equation, are not all simultaneously solvable, given that this one doesn't lie on that line. Think about it that way.
First of all, let me congratulate that you have and appreciate you have given very excellent and a very nice lecture. Despite of such a difficult topic, to understand the W boson that goes on is not that easy. And you have put it in such a manner that you have built up a story right from the beginning. And you find the element that which has been coined by Aristotle, and then with report scattering, and then models, and then you have so and so forth, and then till the end, the happy end. This is very good. So I'll just come to the straight away one question, very small question. During your experiment, you have mentioned about the detector like MWPC, multi-wire proportional counter. Because this has recollected some of the memories, because this has been discovered by the Professor Karpak, to whom I met him in 1991 personally. That time he was not a Nobel laureate, of course. He got the Nobel Prize in 1992. So I just want to understand the mechanism that how this detector being used in the detection of the W boson.
Okay.
Whether the same mechanism that is being used in the charged particle that we detect.
Pretty much. This technology has improved in accuracy. It has improved in a couple of accuracies. Timing accuracy and position accuracy, the two things we care about. But fundamentally the principle is the following. Here is a high voltage wire, positive voltage. This is the positive voltage wire. This is a negative voltage wire. So now each charged particle comes through like this. So what does it do? It hits the atoms of the gas. So these wires are all placed in some gas. Argon, carbon dioxide, many different gases. Big signs there. So what happens when the charged particle of high energy hits the atoms? It knocks out the electrons of the atoms. So that is just called ionization. So what happens to the electrons that are knocked out and the positive ion that is left behind? Well, this is a positive ion, so it is attracted to the negative voltage wire. The electrons being negative are attracted to the positive voltage wire. So we have just seen the drift of the electrons this way and the ions that way. The time with which the electrons take drift from there to there is clearly just simple equation. If you measure the drift time, say it is 5 nanoseconds or 20 nanoseconds or 50 nanoseconds, typically we are now able to measure it with 1 nanosecond accuracy, so 1 billionth of a second accuracy on the drift time. If you now know the drift speed, so you have to separately go and study your chamber and know exactly what is the speed with which the electrons are drifting, you simply apply this and you say drift time measured by drift velocity is the drift distance. Therefore, if you know the position of the wire accurately and you are able to calculate this particular drift time and therefore the drift distance accurately, the simple math will tell you, you know this position accurately. And that is what it is. We simplify it a lot. But knowing the wire positions and the drift velocity and the time, the basic ingredients allow you to say where exactly did the charged particle comes through, and we want to measure this thing with some high accuracy, and therefore all these ingredients have to be known with high accuracy. Basic physics, but you just have to know everything very, very well. So what has happened over the decades since Sharma did this is all of the accuracies we are talking about here have steadily improved. The accompanying improvements in electronics and all the other technological improvements.
Hello. Hi. You talked about the W mass being different, what the standard model had predicted. I have two questions. The first is, what does it mean for the mass of the other bosons and of the other fundamental particles? So specifically speaking, let's say for instance, you have shown in your own analysis that you checked for the z using your method, and for that you got the value would be the standard model had already predicted, right? So showing that your method works. Now, before this analysis, W's mass had also been already established to certain value that the standard model had predicted. So I'm assuming that also had certain sigma, which was, and therefore it was accepted. And in this method, you have shown that the z using your method has the value that we have had so far. Can we say that in the future, with more statistics, can we expect the mass of the z to be different from what even what your own method has shown right now? That's the first question. The second, so in your analysis, you have used the missing 80, the neutrinos, to calculate the W mass. And you said that it's because of the missing neutrinos that it takes long time to do the analysis. But the W also decays to quarks, so the analysis could have been done hadronically as well, I suppose. But since you didn't, I'm assuming it takes probably longer or is more difficult. If that is the case, how do you compare the analysis of the hadronically decaying W to leptonically decaying W? Would it have been more difficult? And if yes, then why or in what way?
So, this particular measurement, so this is not a calculation, this is a measurement of the Z boson mass from the previous collider. So, the accuracy with which that was measured is 2 MeV, so 91,188 plus or minus 2. So you ask, can the running colliders, the Coriolis collider which is now stopped, if you have the data, can the CERN collider, can the available colliders at the moment improve on the accuracy of this number, which is plus or minus 2, I did not write it, but that's plus or minus 2, that we already have from the past collider. You will notice that at the moment this analysis has plus or minus 8. So the question is, can we improve from the plus or minus 8 to something better than plus or minus 2? This is probably not, first of all, it is not clear it is useful. So, the usual thing, something can be done, but it has to be useful, then maybe you should invest.
Okay, so the question was if, so what does it mean for the masses of the other fundamental particles or the other bosons? So because every particle I'm thinking will have, every particle that we detect may have gone through some quantum fluctuation during the interaction process. So the quantum fluctuations which you are basing for the W mass, so it could affect the mass of every other particle that we know so far. But right now, you say that the Z is a certain value. Could we expect in the future these masses to be also different?
I think I understand the question better. It is in fact true that just like the W boson is experiencing quantum fluctuations, the Z boson is also experiencing quantum fluctuations. So, this accurate number, which we are not able to reach yet, and I'm not sure we will reach without a new collider of this type, which we don't have at the moment, but there are some plans. This particular mass measurement, which is already made in nature, so that's the number of the Z mass in nature, like the W measurement, is already including all the quantum fluctuations happening in nature. Okay. So, in a sense, the W boson mass is telling us that there are additional quantum fluctuations because the calculation without the quantum fluctuations is disagreeing with the measurement. So you have to apply that logic and say, do we have a fundamental prediction of the Z boson mass with and without those quantum fluctuations, so that you can compare and say, I can sense the additional quantum fluctuations. So notice that the inference of missing quantum fluctuations is completely dependent on a calculation with them and a calculation without them. So now your question becomes, is there a calculation or you can make of the Z boson mass with certain quantum fluctuations and without? And the answer is no. The answer is no. The reason is there are fundamental unknowns in the standard model. Those unknowns already incorporate the quantum fluctuations, and those unknowns are already being constrained by this measurement. So maybe I'll give a shorter answer. I gave this analogy of linear equations, right? So one equation, two equations, three equations. If you have two equations and two unknowns, they intersect at a point. You have no more predictive power. The two unknowns are determined by the two equations. So now you ask, is something else going to change that intersection point? And the answer is no. Those two lines will continue to intersect there. What the W mass is saying is now we draw a third line. Is the third line going through the intersection of the first two or not? So either the third line goes through the intersection or it doesn't. But the intersection of the first two lines is not changed. And in some sense, that's the answer to your question. One of those intersecting lines is a Z and it's already fixed. So it doesn't move. Right? The second line does not move because the third line shows up. Think about it. That is sort of what is the way to look at it. Doesn't change every other fact. Sorry, the second question was, can we use the quark decays? Yes. So it is indeed true that the W boson theory interacts with quarks. And we said that early on, that is exactly how the proton turns into, a neutron turns into a proton, because the quark in the neutron is turning into the quark of a proton, and that's exactly how the weak decay happens. So it has to be true that the W boson interacts with quarks, therefore it can decay to whole. The experimental problem is that when a quark shows up in the experiment, there is no such thing as a free quark showing up in the experiment. So that is a completely different discussion. We'll need another half hour for it. Why the strong interaction remains confined inside the proton and the neutron. So this is the entire logic of confinement. So because free quarks do not show up, in the end their energy shows up all in a whole bunch of particles that come out. So there is 5, 10, 20 particles coming out.
The question is whether you could use jets to do the analysis.
So just to explain to everybody why we are saying jet. The decay to the quarks is actually manifest into the W boson decay into 20 particles like this and 20 particles like this. And those 20 particles are forming a jet-like object, like a spray of particles and another spray of particles. So now the question is, can we measure with this kind of accuracy when we are measuring one particle, the electron, with 10 to the minus 4 position? Can we measure all those 20 particles with that same accuracy? The answer is no. So the neutrino problem does not exist because now everything is visible. But the fact that what is visible is measured with much worse accuracy than this fundamentally makes it useless. You never achieve that accuracy for the
So let's move to
quark
the next
jet level.
question after this, because looking at the time and people are interested, so just we'll move to the next question.
Yes, please.
Yeah.
Good evening.
Just for curiosity, she is a very brilliant student of Ferguson College, Ekata. We used to teach her different topics in physics, and she used to ask so many tough questions, and it was really a good time for learning for all of us. She gave us a lot of opportunity for us to learn through her questions. Good, Ekata.
So next time she has to come here and I will sit there.
Yeah, she will address that. We will sit there and ask her questions.
Very good.
Okay. Just as Manasi said, we are running short of time. Only one question. Mr. Date wants to ask some questions.
This question and then after
Yeah.
we'll ask the question.
Yeah, after this Date, so we'll ask one question and then we'll go ahead.
So good evening, sir. It was a very nice session and a very deep knowledge sharing. We were able to pursue many things from your lecture. So thanks for that. I am Dr. Eknath Ayatollah from Zee Institute, Pune. Actually, at one point of time in the lecture, you told that don't ask the question where the energy came from during the Big Bang. So you might have thought about that. So I wanted to know what are your interpretations about where the energy might have came from.
Yeah. So my answer or my level of understanding is the following. You have to always question the question. In other words, the source of your question is a belief that energy is conserved. Right? So the total amount of energy is fixed, and therefore we ask the question, if suddenly some energy shows up on nowhere, then how can it show up on nowhere? Because the total is fixed. It's like money, right? If I suddenly get $2 in my pocket, you have to ask the question, somebody must have given it to me, so $2 are missing there, because I'm not printing money, right? I'm not a counterfeiter. So nature to our understanding, by certain logics is not a counterfeiter. The energy has to come from somewhere. So what is that logic? That logic goes back to a very famous mathematician, scientist, lady actually, Emmy Noether, who was a student of David Hilbert, one of the creators of quantum mechanics. And she has a famous theorem named after her, which maybe probably had contributions from David Hilbert, which is called the Noether theorem. So you have to ask the question, what is the statement of that theorem, and how does it predict that certain quantities like energy and momentum are conserved? What is the reason for the conservation of energy? In a very few words, the reason for energy conservation is that the laws of physics are working in an environment which does not depend on time. We call that time invariance. In other words, if you look at the laws of physics today versus tomorrow versus day after, they are the same laws of physics. The environment in which the laws are working do not depend on time. It's time independent physics. The independence of time is an input to Noether's theorem, and you ask what will the theorem then say is the output. If time independence is given, energy conservation is the result of Noether's theorem. It's a theoretical, mathematical connection between independence with respect to time that leads to energy conservation. Now you ask the question, is that a valid input to the Big Bang? Certainly not, because in some sense time and space are starting at the Big Bang. So before the Big Bang versus after the Big Bang, things are certainly not independent of time. And therefore, by Noether's theorem, there is no reason for energy conservation. You see what I am saying? I am saying that the precept for energy conservation is taken for granted because we live in essentially a static universe. Although it is expanding on the cosmic scale, from day to day it is a static universe. So the static universe is the reason according to this theorem. It's a very deep theorem. It explains all the things that are called conserved quantities. Why energy is conserved, why momentum is conserved. Because there is a property of nature that it doesn't depend on where you are in space or where you are in time. That independence manifests itself as energy conservation and momentum conservation, for example. And all conserved quantities, electric charge, why is it conserved? It comes from Noether's theorem too. So when time independence is not true, at the time of the Big Bang definitely, then the whole idea of energy conservation is a meaningless concept. It's not a conserved quantity anymore. So where it comes from, it's not a conserved quantity, it can just be just like that. In other words, why don't we all have $1 trillion in our pocket? Because according to the laws by which we all agree to be citizens, we cannot print money. So it's a conserved quantity. Somebody prints and that's the amount of money there is. But if you all had a printing press, somebody asked you, you didn't have $1 trillion yesterday, today you do. How? There's no rule to prevent printing, so you can print. This is what the Big Bang did, right? It just printed energy. There's no rule to prevent.
Before questions, I want to thank you on behalf of all listeners for the very, very excellent oration. There are two questions. Just like W boson measurement, do you have any plan to measure Higgs boson again? Because I think that instead of the standard model value of 125.35, it might be 125.39 and plus GeV. So is there any plan like that, measuring W Higgs again? And second question is, as we are duplicating the conditions of the Big Bang, we might have produced particles of dark matter, yes. And that value can be between the temperature range of 10 raised to 13 or 10 raised to 14 Kelvin. Yes. So shall we search again from all the data from the dark matter, the particular energy level?
I'll answer the second question first. Most logical answer for the production of dark matter is in fact it is a new kind of particle, we do not know about it. But such particles have some kind of interaction that we don't know yet, but maybe the W boson is sensing it, so dark matter is a candidate for this exploration. And so some interaction between known particles and dark matter particles, if it is present now, because the W is sensing it, it must also be present in the past and the future, and therefore it was present at the time of the Big Bang. And therefore, when all the other particles were being produced with the Big Bang's energy, at that time the dark matter particles would also be produced. And that is why they happen to be around. So this is a quick answer for how dark matter happens to be present today. And so if we were able to reach the energy of that we needed at the time of the Big Bang or soon after, at which the dark matters were produced, if such an energy were achieved at the Large Hadron Collider, then it is absolutely correct what you say, that the LHC would also be able to produce dark matter particles. So this is a big field of research, among other reasons, why the LHC continues to operate and why there is a big plan to operate LHC for 120 years. And one of the projects I am very much involved in and thinking about is, if dark matter was produced at the LHC, how would we detect it? It is dark, so obviously it's difficult to detect. So we have to have some new technology to find a particular signature that you will identify and say, this looks like the dark matter production signature and not something else. You have to have the unambiguous proof that this is dark matter production. So, in fact, detection of dark matter at LHC is a big thrust, including mine. Your first question was, is the Higgs mass worth measuring more accurately? I think the answer is no. The entire motivation for measuring some of these particles more accurately is in the logic of the linear equations, that you are either making one of those equations more and more accurate. In other words, every one of the equations is like a band. If you make the band narrower and narrower, the intersection of the lines become more and more precise. So which you are able to say either the answer is here or it's not. If every one of those lines were fuzzy, sort of a thin line, it was a thick line, that's the statement that your experimental measurement is not so precise, so the line is bad, which means the intersection is not able to be pinned down accurately. The line associated with the Higgs boson mass is already so thin in this language that it is no longer limiting the precision with which you are asking the question, are they all intersecting at a point or not? So the consistency of all these different measurements, are they consistent or are they not consistent? You will not improve that question anymore by making the Higgs boson mass more accurate. Not worth it, therefore. The other measurements are worth exploring because they will help to make this question more precise. Further measurements of the Higgs boson mass will not help in making it more precise.
Thank you, sir.
So one last question.
प्रश्न मराठीत विचारतोय कारण सो जर तुमचे ऑब्झर्वेशन स्टँडर्ड मॉडेलनुसारच निघाले असतील तर डार्क मॅटर आणि ह्या सगळ्या गोष्टींना घडून पुढचे जे काही प्रयोग होणार आहेत ते काय झाले असते किंवा डार्क मॅटरचं एक्सप्लेनेशन कसं आलं?
ह्याचा अर्थ काय काढला असता की डार्क मॅटर हा चित्र दाखवतो. डार्क मॅटरची इंटरॅक्शन डब्ल्यू बोझॉनशी होते की नाही हा प्रश्न आहे. या लॉजिकमध्ये ते चित्र कुठे गेलं, इथे कुठे गेलं, ह्या लॉजिकमध्ये हा एक्स पार्टिकल जर डार्क मॅटरचा असला त्याची इंटरॅक्शन डब्ल्यू बोझॉनशी होते म्हणून हा पर्टिक्युलर क्वांटम बबल तयार होतो. त्याचा इफेक्ट आपल्याला डब्ल्यू बोझॉनच्या मेजरमेंटमध्ये दिसतो असं म्हणता येईल. जर डब्ल्यू बोझॉनची मेजरमेंट ह्या दोन कॅल्क्युलेशन बरोबर एक्झॅक्टली इक्वल आली असती ह्याचा अर्थ आपल्याला हा इफेक्ट दिसत नाही. ह्याचा अर्थ असा करता येतो की एक्स पार्टिकल ची इंटरॅक्शन डब्ल्यू बोझॉनशी होत नाही. ह्याचा अर्थ दिस बबल डझंट एक्झिस्ट. त्याचा अर्थ असा होत नाही की एक्स डझंट एक्झिस्ट. इट जस्ट मीन्स दिस पर्टिक्युलर इंटरॅक्शन हिअर इज नॉट हॅपनिंग. ह्याचा अर्थ की डब्ल्यू बोझॉन इज नॉट सेन्सिटिव्ह टू डार्क मॅटर इन दॅट सिनारिओ. तसं झालं असतं. इथे असं दिसतंय की डब्ल्यू बोझॉन मे बी डार्क मॅटरचा सेन्स करू शकतो.
ओके, पण मग जर डार्क मॅटर एक्झिस्ट करतो तो एक्झिस्टन्स होत नाही तर मग त्याचं एक्सप्लेनेशन फक्त CMB किंवा अशा प्रकारे होऊ शकतं.
आता डार्क मॅटर जितकं डार्क होत जातं, डार्कचा अर्थ इंटरॅक्शन होत नाही. सो आपण त्याला डार्क का म्हणतो की त्याची इलेक्ट्रिसिटी आणि मॅग्नेटिझम इंटरॅक्शन होत नाही, म्हणजे लाईट फक्त इंटरॅक्शन होत नाही. इथे हा दुसरा फोर्स आहे, त्याची इंटरॅक्शन होऊ शकते. ही इंटरॅक्शन पण तुम्ही कॅन्सल आउट केली त्याचा अर्थ त्याच्या इंटरॅक्शन कमी कमी होत चालले. ऑप्शन आर रिड्यूस आहे. आता डार्क मॅटर जर खरंच डार्क निघाला म्हणजे कुठच्याच स्टँडर्ड मॉडेल पार्टिकलशी इंटरॅक्शन होत नाही असं जर कळलं तर आपल्याला डार्क मॅटर कसं दिसणार बिकम्स टू बी डार्क. पण त्याच्यामध्ये एक प्रॉब्लेम आहे. मग असा प्रश्न निघतो की बिग बँगच्या वेळेला डार्क मॅटर तयार कसं झालं. आता इंटरॅक्शन नाही म्हणजे तेव्हा पण नाही. इंटरॅक्शन असली तर तयार कसं होईल. सो कुठेतरी काहीतरी इंटरॅक्शन असावी असा अर्थ निघतो, बिकॉज इट इज देअर. आणि दुसरं म्हणजे किती डार्क मॅटर आता आहे आणि किती विजिबल मॅटर आहे ह्याचं प्रमाण 1 to 5 आहे. तर 1 to 5 प्रमाणाचा अर्थ थोडासा नॅचरली असा वाटतो की काहीतरी इंटरॅक्शन असावं. नाहीतर प्रपोर्शन 1 to 5 का नाही, 1 to million निघू शकलं असतं, 1 to 1 billion निघू शकलं असतं, काय वाटेल तर नंबर निघू शकला असतं. 1 to 5 इज अ सजेस्टिव्ह नंबर की काहीतरी इंटरॅक्शन आहे. सो डब्ल्यू जी नसती तर दुसरीकडे तरी शोधू नये. सो असं एक आहे म्हणणं की डार्क मॅटर टू बी पार्ट ऑफ अ डार्क सेक्टर. तो सेक्टर किती डार्क आहे म्हणजे त्या सगळ्या पार्टिकल्स आपल्याकडे सगळे भोवती फिरतायत ते, पण त्यांची आणि आपली इंटरॅक्शन कमी कमी जर होत राहिली तर ते सेन्स करणं कठीण होत जाणार. पण नेव्हर से नेव्हर असं न्यूट्रिनो कधीच दिसणार नाही असं म्हटलं होतं. 20 वर्षांनी न्यूट्रिनोचं डिटेक्शन झालं.
थँक्यू सर. क्वांटमपासून मल्टिवर्सपर्यंत जर्नी करणार. थँक्यू.
Really, thank you very much, sir. In a time of delta t equal to 90 minutes, you gave a lot of attention. So we are towards the end of this program. Everything has a beginning and an end, including universe. So after the thanks proposal, there will be Vande Mataram. This Vande Mataram is of 6 cantas. So it is not 2 stanza, it is 6 stanzas. So after the vote of thanks, we will immediately stand up for Vande Mataram. There are 2 instructions. Some people have come by a bus. Those people should leave the hall by that door and scan the QR code there and write the answers of the questions asked, so we will have your information. Other people will leave by this door. Again, they will scan the QR code there, so we will have your information. I now invite Dr. Manasi Malgaonkar to propose vote of thanks, and then after that, so Kirti Unthekar will recite Vande Mataram. Thank you.
Namaste. Basically, I do not want to propose vote of thanks. I'll say I would like to remain in debt of all of you and would like just to propose a gratitude or gratitude from Vigyan Bhakti. So I thank Professor Ashutosh Kotwal for accepting the invitation and for allowing us to organize various talks, press meets and the visit in physics department, and also for such an insightful, intellectual and thought-provoking session. I wish to extend my gratitude firstly to the chairman of DA's governing body and council for accepting our request to organize this program jointly. I would also like to thank Principal of Ferguson College, Dr. Pardeshi sir, for extending all possible and desired help for the successful conduction of this session. I would specially thank Dr. D.A. Kulkarni, Dr. Swati Zogalkar and Dr. Nandakumar Mande, along with the faculty of physics, researchers, students of physics department of Ferguson College. These were the basically backbone of organizing this oration. I will not forget the contributions and assistance received by Dr. Somogray Chaudhary for accepting our invitation to organize technical session which was held yesterday for physics, astrophysics, astronomy fraternity of all over India at Aluka. I also thank Dr. Kandaswamy for conducting that particular session. I thank Shri Gitesh Doshi for the live broadcasting, recording and photography of this session. I also thank all other faculty members and staff members of Ferguson College as well as Deccan Education Society for their help and the participation. I wish to extend my gratitude to all the journalists, media houses who were present yesterday and present today for the wide publicity. I cannot forget the efforts taken by Mayuresh Prabhune and Sanjay Maikar for this publicity. Our Viva member and Vice Principal of Wellington College, Dr. Sunil Kulkarni, and our senior Karyakarta, Shri Shrikant Kulkarni, should not go without mention for their wholehearted involvement. I would also like to extend the gratitude to all the family members of Kotwal sir for helping us in many ways. and allowing Dr. Kotwal sir to spare his valuable time for this cause. Last but not the least, I thank all the audience present here and who have joined online for this session, as well as yesterday who had joined online for the session. If I have forgotten to thank anyone, please consider it as my inability and accept the wholehearted thanks to one and all from all the organizers. And now I thank in advance Kirti madam, who will be reciting the full Vande Mataram now. Thank you. ॲक्च्युली एक अनाउन्समेंट आहे. आपण जरा सरांबरोबर फोटो काढून घेऊया. तर ऑर्गनायझर्स पैकी मी सगळ्यांना विनंती करते, जरा स्टेजवर येऊ, आपण एक ग्रुप फोटो नक्की काढूया. कुंटे सर, परदेशी सर, या ना, डी कुलकर्णी सर, स्वाती मॅम, जयंत